Okay, now let's try to solve this circuit, okay, which includes a voltage source and an inductor and a resistor, a set of inductor and a set of resistors. The voltage source is 18 volts and the frequency is 80 kilohertz. We have three resistors R1, R2, and R3, and two inductors L1 and L2. Okay, and the first thing that we can do here is to solve for omega, which is equal to 2 pi f, which is equal to 160,000 pi hertz, which will be equal to 503 kilohertz. Okay, now that we know that, the next step is to simplify our first circuit, which is this one. These two are in series, and we are going to solve for the equivalent admittance Y1, but in order to do that, we also need the equivalent inductance, equivalent impedance, okay, which is Z1. So Y1 is just equal to Z1. Okay, so first let's solve. So let's combine R3 and L2. Okay, since R3 is real value, then L2 is part of a complex. Now is the complex component of Z1. Then we can write Z1 is equal to R3 plus omega L2J. Okay, and Z1 is easily solved as 5.6 kilo ohms plus 4.02 kilo ohms J hat. Okay. Let's get the absolute value of Z1. Z1 is 6.89 kilo ohms, and its phase angle, okay, which is equal to, if you recall, XC minus XL over R, where XL is just your 4.02 kilo ohms. So this will give us 35.7 degrees. Okay, so now we can get Y1, okay, and this is the reciprocal of Z1, and we already know how to solve it from the previous problem. So this is the absolute value of cosine theta over the absolute value of Z1 minus sine theta over the absolute value of Z1 J hat. So from there we can get Y1 to have a real and imaginary components of 0.118 millisiemens minus 0.0846 millisiemens J hat. Okay, so this is our Y1, and we can also solve for this corresponding admittance, and this is quite simple because there's no complex component. So number 2, we solve for the corresponding admittance of R2. So solve for Y2. So let's say Y2 is equal to G2 divided by 1 over R2. And Y2 is just equal to 0.303 millisiemens. Okay, now that we have these two, okay, we can then combine them, okay, to get Y3. Okay, so we now solve for Y3. And Y3 is just the sum of these two admittances. Okay, so Y1 has a real component, and y2 is just a real component, so we just add that, and then y3 will only get the real component, or the complex or the imaginary component from y1. So y3 is equal to 0.421 millisiemens minus 0.0846 millisiemens J. So the next thing that we need to do is to solve for Z3, or let's say Z2 instead, because we don't have Z2 yet. Z2 is just the reciprocal of Y3, and we already know how to do that simply by using this equation here. Okay, so just to complete the procedure, we need to get Z2, which is equal to 1 over Y3. So Z2 is equal to 2.28 kilo ohms plus 4.59 kilo ohms J hat. Okay. Now we can combine Z2 with L1 because Z2 is in series with L1. You cannot combine Y3 with L1 because Y3 is the admittance, and it's solved by getting the parallel, or by solving for the equivalent parallel circuit. So Z2, okay, we combine with L1 by doing this. We get Z3, okay. So just to complete, solve for Z3. So we get Z3 equal to Z2 plus omega L1 J hat. Okay, and then we get Z3, okay, which is combination of this. So this is Z3, okay, and Z3 will have a value of 2.28 kilo ohms plus 5.49 kilo ohms J hat. Okay, now again, Z3 is an impedance that was solved using a series circuit, but this equivalent circuit is in parallel with R1, so we need to get the reciprocal of Z3 first, okay, in order to solve for the equivalent of Z3 with R1. Okay, so what we are going to do next is to get Z3, or Y4, which is the reciprocal of Z3, okay, and then combine that with Y5, which is the reciprocal of R1. Okay, simplify. The next step is 5. Simplify R1 and Z3. So to do that, we need to get Y4, which is the reciprocal of Z3, and that's easily solved to be 0.065 millisiemens minus 0.155 millisiemens J, and then Y5 is nothing but 1 over R1, okay, which is equal to 0.833 millisiemens. And then we get the Y total to be equal to 0.898 millisiemens minus 0.155 millisiemens J hat. And finally, we can get the equivalent impedance, okay, by taking the reciprocal of Y total. So this will be equal to 1.08 kilo ohms plus 187 ohms J hat. the absolute value of Z total is equal to 1.097 kilo ohms, and its phase angle is equal to 9.82 degrees. Okay, and just for completion, let's solve for the current. So the current is equal to V sub S, okay, divided by the Z total. V sub S here is 18 volts and Z total is 1.097 kilo ohms. So the current is 16.4 milliamperes. Okay. If we do all of this in MATLAB, we can immediately solve for the phasor diagram of the circuit, the equivalent phasor diagram of the circuit. So again, this is the real component and this is in ohms. The imaginary component is also in ohms. Okay, we see that Z has a total of 1080 kilo ohms, and here the complex or the imaginary value is about 1.87 ohms. The magnitude of Z can easily be computed to be about 1100 kilo ohms.